Well, welcome to the first video lesson in Unit 5.3 in our study of electromagnetic waves. In this unit of study, our emphasis is going to be on the nature of light and the way in which all forms of light, ranging from radio waves to microwaves to infrared to ultraviolet, visible light, and so on, are nothing more than electric fields and magnetic fields oscillating together. In order to describe electromagnetic radiation as oscillations in electric and magnetic field, we're going to need to employ a lot of the major concepts and formulas that we've learned along the way, starting with Gauss's law. Now, you know Gauss's law for electricity as a statement that the net amount of electric flux through any surface is equal to the amount of charge that resides within that Gaussian surface divided by the permittivity of free space. So you could apply this to a situation like, what if you had a plastic rod that was rubbed with a piece of fur and gave it a uniform charge density? So if this piece of plastic is all charged up, can you figure out how strong the electric field is at this point? There's a second version of Gauss's law for magnetic fields, and it says the total amount of magnetic flux through a closed surface is equal to 0. That's really a statement that there are no magnetic monopoles. Take, for example, this bar magnet pictured here. You can't cut the bar magnet in half and expect to have an isolated north pole. At the place where you cut it, you'll form a new south and a new north pole. After all, the behavior of this bar magnet is really just dependent on the alignment of magnetic domains within the material. And if the magnetic domains all line up in the same direction, then no matter how small you cut the magnet, every place you cut it, you form a magnetic dipole. So let's try to apply Gauss's law here. What if we made a closed surface that only enclosed the north pole of this magnet? Would there be a net flux that's non-zero? Let's draw some magnetic field lines. Well, a magnetic field line is going to come out of the north pole, then it's going to puncture or penetrate this Gaussian surface and travel onward. So there's some outward flux, and there's another field line curving this way, and it punctures through our Gaussian surface and carries on. Oh, so let's see. Now I know these field lines are going to eventually curve and come into the south pole. So you see we have outward flux but no inward flux. So it looks like the net flux isn't 0, but that's foolish thinking. We know that these magnetic field lines don't actually end here at the south pole. The field line carries on through the magnet, and sure enough there it penetrates the Gaussian surface as it travels in and continues on to form a closed loop. So for every bit of outward flux, there's some inward flux to cancel it out, and so the net flux indeed is 0 due to the fact that there are no magnetic monopoles. So we're going to employ Gauss's law in our study of electromagnetic waves. We'll also apply, what are some other key laws we've described along the way? How about Faraday's law? That'll certainly come up again in this unit. So here's a statement of Faraday's law. If I want to know the voltage around a loop, I could say there's a positive high potential at the positive terminal and a low potential at the negative terminal. And as you go around the loop, then there's a potential difference across this resistor that can drive a current and power it. But there's another way to power this resistor without a battery. If I take a bar magnet and thrust it back and forth, here there's a small amount of flux, more flux, increasing flux. So constantly changing the flux through the loop generates electricity. And if we go from point P back around to where we start, normally Kirchhoff's loop rule would say that there's no voltage around that loop if there's not a battery. But if the magnet's in motion, there is a voltage around the loop. Now, how do we calculate voltage around the loop? Because we're going all the way around a loop, we'll take a closed loop integral, and voltage is the product of electric field and distance. So we can say voltage is the integral of E dot ds. And that voltage applied around the loop that doesn't contain a battery is entirely dependent on how quickly the flux is changed. In other words, it's equal to the rate of change of the magnetic flux. And we've got to throw in a negative sign as a reminder of Lenz's law and the direction of current that would be induced. So there we have it. Gauss's law for electricity, Gauss's law for magnetism, a statement of Faraday's law. I think in the past we've just said this is a voltage in EMF, and that's exactly right. Here we're writing it a little more explicitly. Okay, what's another major law we've learned along the way? Ampere's law. Ampere's law says the integral of not E dot ds, but B dot ds is equal to mu naught multiplied by the amount of current enclosed by some imagined loop. We'll take a look at this circuit in a moment. Let me move that out of the way. Let me show you an example of how we might apply Ampere's law in the past. Maybe we want to find the magnetic field near a current carrying wire. So we imagine some current I flows to the right, and I want to know the magnetic field at this point P. So we can make up an imagined loop, call this our Amperian loop, and that loop can be broken up as a path into a bunch of little bits of displacement. So each of these little vectors ds gets us a fraction of the way around our loop. So if I take the product of the strength of the magnetic field as it coincides with any of these path elements, the net value, if I integrate all the way around the entire imagined loop, should only depend on the amount of current that that loop encloses, which in this case would be all of the current, since it passes entirely through the loop. By choosing a circular loop and making it concentric with the center of the wire, the left side of this equation becomes a very simple calculation. It's just B times the circumference of the loop, which would be 2 pi r. That's equal to mu naught times the full current enclosed. Therefore, the magnetic field at this point P is equal to mu naught I over 2 pi r, and that's most certainly a familiar expression. So let's apply Ampere's law to this case. Before we wrap up this lesson, I'll challenge you to see if you can recall all of these laws without looking. Gauss's law, Faraday's law, and Ampere's law. So, continuing our discussion of Ampere's law, what if you had a circuit with a battery and a capacitor and a switch, and you closed the switch? Now, here's an investigation that might be worth checking out. What if you put a compass needle right here once the switch is closed? In what way will the compass needle deflect? Well, the current is going to conduct in a clockwise direction. What's really happening are electrons. They're the free particles to move. Whatever free electrons were in the upper plate of the capacitor drift toward the high potential side of the battery. But electrons drifting in a counterclockwise direction is consistent with conventional current flowing in a clockwise direction. And now you can apply the right-hand rule. Based on the right-hand rule, point your thumb in the direction of this current in this segment of the wire, and then imagine wrapping the fingers of your right hand around the wire. Once you find that your fingers point out of the page, in other words, right at this point, there's a magnetic field out of the page, and so the compass needle wants to point out of the page. And if you put the compass needle right here, again, you'd find magnetic field points out of the page. I suppose that means just as well that magnetic field would point into the page here. What if you put your compass needle here? Magnetic field would point out of the page, right? Point your thumb downward, wrap your fingers around, and your fingers are coming out of the page. Over here, they're pointing into the page. So as long as we place our compass anywhere near a region where current is being conducted, we'll verify that there are magnetic fields pointing out of the page in the regions outside of our circuit loop, and magnetic fields are pointing into the page in the regions inside. But what about here where there's no current? The current can only conduct through the wires, but there's no current in the insulating space between the plates. So it seems like there's magnetic field near the wire, and it's all pointing into the page. Do those magnetic field lines suddenly disappear and then reappear again over here? In other words, if you take the compass needle and place it here, will it deflect and show that there's magnetic field pointing out of the page right there? This experiment is easy to conduct, and it turns out that magnetic field does point out of the page, even in the region where there's no current being conducted. What we say here is that there's a displacement current. It's as if the current conducting clockwise through the circuit is carried on through here. It's not actually conducted, so this displacement current we need to come up with an expression for. So let's write Ampere's law once again and say that this enclosed current could come in two forms. It could be current conducted in a wire, or it could be this quantity known as displacement current that represents the apparent current responsible for the magnetic field that's sensed in this region in the gap of the capacitor. The integral of B dot ds is equal to mu naught times conduction current plus displacement current. How do we calculate displacement current? Well, current is always measured in coulombs per second. It's a rate of flow of electric charge. So let's think about the amount of charge that resides on these plates. As long as current is flowing, charge is still building up. And if charge is building up, then the electric field between the plates is not a stationary field, it's an increasing field. The electric field is growing in time as the circuit charges up. So let's see. Charge, how can we calculate this? How about let's start with just a calculation of what the electric field is in this space. Electric field is equal to, well, if electric potential is electric field times distance, then electric field is voltage divided by plate separation. But then again, there's a relationship between charge, voltage, and capacitance. So I can replace voltage with Q over C. So the electric field is Q over C times D. In this case, I'm picturing the capacitor as a parallel plate capacitor. So I can replace C with, you know, the capacitance of a parallel plate, isn't it epsilon naught A over D? So this becomes E equals Q over epsilon naught A over D times D. The D cancels out. If we cross multiply, we have Q equals epsilon naught times the product of E and A. So the displacement current is the rate of change. So it would be equal to epsilon naught times the rate of change of the product of E and A. But what is the product of E and A? Well, that's a form of flux. It's not magnetic flux. This is electric flux. So here we have it. We can say that displacement current is equal to permittivity of space multiplied by the rate of change of electric flux. And when we substitute that back into our expression for Ampere's law, we get the integral of B dot ds equals mu naught times conduction current plus mu naught times epsilon naught times the rate of change of electric flux. Something fascinating here. There's a bit of symmetry in these laws. Peeking back at Faraday's law, it suggested that a change in magnetism produces electric fields. Well, this full version of Ampere's law that accounts for displacement current says a change in electric field has a way of producing magnetic fields. So this gets back to the very nature of electromagnetic waves. A radio wave, a microwave, X-rays, gamma rays, visible light, you name it, they all have at their heart oscillating electric and magnetic fields that reinforce each other in perfect accordance with the full version of Ampere's law and Faraday's law. So before we sign off on this video lesson, probably a good time for you to see if you can write down off the top of your head these statements of Gauss's law, Faraday's law, and the full version of Ampere's law. So Gauss's law for electricity says the closed surface integral of EdA, in other words, the total flux, is equal to the charge inside a Gaussian surface divided by epsilon naught. The full surface integral of BdA must be equal to 0 because there are no magnetic monopoles. So for every bit of outward flux, there's always an equivalent amount of inward flux to cancel it out. So we have integral of EdA and the integral of BdA. Faraday's law is a closed loop integral of E ds. So what remains? Ampere's law is a closed loop integral of B dot ds. Okay, and what does Faraday's law say? Well, the integral of E dot ds is really a way of calculating voltage, and Faraday's law is about inducing voltage as long as there's a rate of change of magnetic flux. Of course, the negative sign always belongs in there to remind us of Lenz's law. Ampere's law we now have a full version of. It says that the integral of B dot ds is equal to mu naught times the amount of current enclosed by the Amperian loop. That current could be a conduction current, or it could be a displacement current, where displacement current is epsilon naught multiplied by the rate of change of electric flux. So, once again, note the symmetry. A changing magnetic field produces oscillating electric fields, and a changing electric field makes for changing magnetic fields. So we'll carry on with that idea in an upcoming lesson to see if we can derive an equation for calculating the speed with which light propagates.